Welcome to Electron Line, and now we're going to find out how to calculate the distance to the first maximum and the second maximum. So what is the distance y from the central maximum to this distance, and from there to the second distance? So we'll call that y sub 1 and y sub 2. So y sub 1 here, and this distance right here, let's call that y sub 2. And what is that equal to? Assuming that the distance from the diffraction grating to the screen is 2 meters, L, we still call that L, and the distance between any two adjacent slits is 2 micrometers, or 2 times 10 to the minus 6 meters. Let's also assume that the wavelength of the light we're using is 500 nanometers, just like we did before. And okay, how do we go about doing that? Again, it's all about the extra distance traveled. So if we take a close look at any two adjacent slits, it'll look like this. So we want to take a look at those two adjacent slits, and so it's all about the extra distance traveled. So the extra distance, if this is d, the distance between the two slits, then this here is the extra distance traveled. Here would be the lookup angle theta, which is the same as this angle theta right there. So this extra distance equal to d times the sine of theta, d of course being the hypotenuse, and this is the opposite side to the angle theta. So the extra distance traveled is equal to the hypotenuse d times the sine of theta. Now, when do you have your first maximum? That's of course when the extra distance traveled equals a whole wavelength. Oop, I just dropped my cap. Oop, there we go. So, for the first maximum, the requirement is that the extra distance traveled equals 1 lambda. So we take d sine theta equals lambda, or sine theta equals lambda divided by d. So in this case, we can find theta, so theta, and of course this is for the first maximum, let's call it theta sub 1, because it's for the first maximum. That's going to be equal to the arc sine of lambda, a single lambda, divided by distance. All right, and when plug in the numbers, that's equal to the arc sine of lambda would be 500, that would be nanometers, divided by the distance, which is 2 micrometers, convert to nanometers, would be 2,000 nanometers. Right, and so with a calculator, let's see what that's equal to. 500 divided by 2,000, that's a quarter, so 0.25, take the arc sine of that, we get 14.48 degrees. So that gives us theta sub 1 is equal to 14.48 degrees. So that's the lookup angle from here to the first minimum. So that's this angle right here. So theta equals 14.48 degrees. Now we need to find y sub 1. Now, of course, what we can say here, that y sub 1 relative to L, that would be the opposite side, that's adjacent side. So we can take the tangent of theta sub 1. So this theta sub 1. So then we can say that the tangent of theta sub 1 is equal to the opposite side, y1 divided by the adjacent side L, which means that y1 is equal to L times the tangent of theta 1. So in this case, that's 2 meters times the tangent of 14.48 degrees. And so again, with our calculator, take the tangent of that times 2 meters, and we get 0.5164 meters. 0.5164 meters. I'm keeping a few extra so-called significant figures because we want to be able to compare that to our next result when we find the distance to the second maximum. But that's at least the distance to the first maximum, which is y sub 1. So now we can find theta sub 2 in the same way. We know that theta sub 2 is going to be equal to the arc sine of 2 times lambda divided by d. Why 2 times lambda? Because we find the first maximum when the extra distance traveled is a whole wavelength. We find the second maximum when the extra distance traveled is 2 wavelengths. So we use 2 lambda divided by d instead of 1 lambda divided by d. So extra distance is going to be 2 lambda in that case. So in this case, this is equal to the arc sine minus 1 times 2 times lambda. That would be 2 times 500 nanometers divided by 2,000 nanometers, because 2 micrometers is 2,000 nanometers. So now we have the arc sine of a half. So 0.5, take the arc sine of that. That's equal to 30 degrees. So theta sub 2 is equal to 30 degrees. And in the same way, we're going to find y sub 2, which is equal to L times the tangent of theta sub 2. So in this case, that would be 2 meters multiplied times the tangent of 30 degrees. And the tangent of 30 is 0.577 times 2 equals, we get 1.155 meters. So y2 is equal to 1.155 meters. Notice that it's probably a little bit more than twice as big as theta sub 1, or y sub 1. So y sub 1 is 0.51, 1.15, that's slightly more than double to get to that second maximum. So you can see that in double slits and triple slits kind of environments, the distance y simply in terms of millimeters, but here we can see that it's 51 centimeters, almost 52 centimeters to the first maximum and well over a meter to the second maximum. So they're spread much, much farther apart because the distance between the slits is much, much smaller. So spreading out that interference pattern, that gives you this particular pattern for diffraction grating. So that's how we find the distance to the various slits. We also find the lookup angles that way. So you see that theta sub 1 is found this way, and theta sub 2 is found that way as well. And that's how we do that.